Good day, students. Welcome to the AP Calc AB free response. We're going to be going over the table problems. We took a look at the 2006 to 2013 table problems, and we extracted some key concepts to create a problem. We're going to be going over the average rate of change, rectangle approximation, fundamental theorem of calculus, linearization, and related rates within the context of one problem. All right, so let's go ahead and take a look at the question. All right, so it says a hemispherical bowl is being drained of water. The radius is modeled by twice differentiable function r of time t. For 0 less than or equal to t less than or equal to 11, the water level is falling. The table below gives values of the rate of change of radius r prime of t on 0 less than or equal to t less than or equal to 11 on r of 6 equals 10. Note the volume of a hemisphere is given by V equals 2/3 pi r cubed, and this is a table illustrating the relationship between the rate of change of the radius at particular times 0, 3, 6, 8.5, and 11. All right, let's take a look at question 1. It says approximate the second derivative r double prime of 4.5 and show the computations that lead to the answer, including your units. So for question number 1, we are approximating r double prime of 4.5. Now you want to note that this is an average rate of change problem. It's not an average value, it's an average rate of change. It's an estimation of the derivative of the derivative. Okay, we're approximating the second derivative here. So this is basically the approximately, it can be approximated by the average rate of change, spell that again. The average rate of change of the derivative r prime of t on the interval containing 4.5. On the interval containing 4.5 is 3 to 6, right? On 3 to 6. So we're estimating the instantaneous rate of change or the slope of the tangent line at 4.5 using the secant line on this interval, okay? So this can be computed, so r double prime of 4.5 can be approximated using delta r prime of t over delta t. This is the same thing. This is the average rate of change in symbolic form from 3 to 6. Okay, so how do you compute this? Not that difficult. You just do r prime of 6 minus r prime of 3 divided by 6 minus 3. Remember calculating the slope of the when you're doing the mean value theorem, if you're calculating the slope of a secant line through the endpoints, this is exactly what we're doing here. Okay, so let's go ahead and finish this off. So that's going to be approximately r prime of 6 is 6.5. 6.5 minus r prime of 3 is 8 divided by 6 minus 3, which is 3. Just plug that in our calculators. I'm going to be making use of a TI-89 titanium calculator for this section. 6.5 minus 8 over 3, answer is negative 0.5 or negative 1/2. Okay, so it's basically approximately negative 0.5. Okay, so this is the approximation of the instantaneous rate of change of the radius at t equals 4.5. All right. Now, something I failed to mention is that problems of this nature are usually calculator active problems. So you're free to use a calculator here for these problems, as you can see me doing right now. Okay, let's take a look at problem number 2. So for problem 2, we are to estimate the radius of the water in the bowl when t is equal to 6.3 using the tangent line approximation at t equals 6. And then we have to determine if it's a lower or upper estimate. Okay? And then we have to give a reason for our answer. All right, so in order to estimate using a tangent line, we need to have the tangent line first. Okay? So let's just write down the steps. So 1, So to estimate using tangent line, to estimate using a tangent line, using a tangent line, first thing you want to do, you're going to first of all, find the equation of the tangent line. Find the equation of the tangent line, and then 2, evaluate the tangent line at a specific point. Evaluate the tangent line at the specific x value, Okay, in this case, the x value we're going to be evaluating the tangent line at is 6.3. Now, do you know what this process is? This is linearization. Okay, that's exactly what it is. All right, so we're using the linearization of the curve to estimate what the output is at 6.3. All right, so first thing we want to do, part 1 is we want to find the equation of the tangent line. Okay, so let's label it 1. Find the equation of the tangent line. Equation of tangent line. All right, so let's go ahead and do that. What's the equation of a line? The equation of a line is what you learned in algebra 1. Point slope form, y minus y1 equals mx minus x1. Okay, so we're looking for the tangent line at t equals 6. That's what we've got from our tangent line, and we're going to use that line to approximate 6.3. Okay, so at t equals 6, we know what our variables are. We know that x1, y1 is basically going to be, we can think of it as t and r of t when t is equal to 6. When t is equal to 6. We have a piece of information here. R of 6 is equal to 10. What does that tell us? R of 6 is equal to 10 implies that this point right here, 6 comma 10 is a point on the curve of R. All right, so what does this mean? It simply tells us that x1 is equal to 6, the x coordinate, and y1 is equal to 10. All right, okay, now we have our x1 and y1. Now next thing we need is the slope to write down the equation of our line. Okay, so m is basically the derivative at x equals 6. So m is basically r prime of 6. So what is r prime of 6? We just simply use our time and derivative relation table to generate what r prime of 6 is. So we can see here that r prime of 6 is equal to 6.5. So the slope is 6.5. Now what is the equation of our tangent line? It's going to be y minus y1. y1 is 10 is equal to the slope m times x minus x1, which is 6. Okay, now let's put this, isolate y so we can evaluate y at a specific x value. So we're going to add 10 to both sides, distribute that, and we're going to have y is equal to 6.5 x minus 29. Okay, all right, so this is the equation of our tangent line, and is also what we can use to approximate or carry out the linearization around a neighborhood of t equals 6. Okay, so we want to evaluate the function. We want to approximate what the radius is at t equals 6.3. So r of 6.3 is approximately what the tangent line tells us the output is at 6.3. So that's going to be what you get when you plug in 6.3 into the equation of your tangent line. So we're using the tangent line to estimate what the function behaves like here. Okay, so it's going to be 6.5 times 6.3 minus 29. Okay, and let's plug that in our calculator. All right, so when you plug into your calculator, you get 11.95. So r 6.3 is approximately 11.95, and the unit is basically meters for the radius. Okay, so that's the radius when the time was 6.3. Okay, now it says, is this an upper or lower estimate? Give the reason for your answer. In order to determine if it's a upper estimate or lower estimate, what we have to do is we have to look at the concavity. Okay, if a function is concave up, then the let me give you the two scenarios here. I'm gonna sketch two functions. So if you have something that's concave up, all the tangent lines will be underestimates. They're going to be basically underneath the curve, and when we make an estimation, they're going to be beneath. For concave up is underestimate. Okay, so concave up is underestimate. And then what if the function is concave down? Okay, if the function is concave down, then the tangent lines will be an overestimate. Okay, so concave down is an overestimate. So just keep that in mind. Concave down is an overestimate. All right, now, what is the situation here? What's the concavity of this function? Is it going to be concave up or down? Well, let's see if we can figure that out. Um, First thing we want to look at is the first derivative. Okay, what is the first derivative looking like around 6.3? The first derivative is falling at that point. Notice how the first derivative is falling. So if r prime of t is less than 0, is decreasing. What does that mean? What does that tell us about r double prime of t? Well, that implies that r double prime of t is going to be negative. Okay, since it's decreasing, r double prime of t is going to be less than 0. Now, if r double prime of t is less than 0, what does that tell us about the concavity? Well, that implies that r of t is concave down. Okay, since whenever the second derivative is negative, the function is concave down, and if the second derivative is positive, it's going to be concave up. Okay, now since the function is concave down because of the second derivative being negative as a result of the first derivative decreasing, then we're going to have an overestimate. This is the situation we're going to be dealing with here. Okay, so let's write that down. The function since the function is concave down, it's concave, and again, it's concave down due to r double prime of t being less than 0, then the tangent line is going to be an overestimate. Is going to be an overestimate. Is going to be an overestimate. To be an overestimate. Okay. So that's that. All right. Let's take a look at question number 3. Question 3, we're to use a left Riemann sum with 4 subintervals to find the integral from 0 to 11 of r prime of t dt. We just state the meaning of our answer in the context of the problem with accurate units. And the question, and also, is this an over or underestimate? Our Riemann approximation, is it going to be an overestimate or an underestimate? Okay, so let's go ahead and set this up. Before we do that, I like to always use a number line for my Riemann approximations so that I can have an idea as to what's happening with the partitioning. Okay, so let's see. We're going from 0, so 0, and then all the way to 3. Let's call this 1, 1, 2, 3. So 3, and then from 3 to 6. 4, 5, 6. Looks evenly spaced so far. 6 to 8.5. Let's make this a little bit longer. So 7, 8, 9, 10, 11, something like that. All right. So we have 6, 7, 8, and then 8.5. It's going to be somewhere right here. 8.5. And then the next is 11. So this is 9, 10, 11. Okay? All right. So this is going to be x1, x1, x2, x3, x4, and x5. Okay? All right, so we are using left Riemann Riemann sum for this problem. So what does that mean? It basically means that we're going to be taking all the points to the left of the right endpoint. So we're going to start from x1 and go all the way to x4. Okay, we're not going to use x5. And then we also have to know the widths of our rectangles, right? So let's see what the widths of our rectangles are here. So that will determine what formula we're going to use, okay? So the width between x1 and x2 is w1. And we can clearly see it's 3 units long. Between x2 and x3 is w2, which is 3 units long. 1, 2, 3. And then between x3 and x4, 6 minus 8.5, 1, 2.5, 2.5 units long. W3 is 2.5. And then the last one, W4 is going to be 2.5 also. Okay, 2.5 plus 8.5 equals 11. All right, so you can clearly see that in this problem, the widths are uneven. Okay, so we have to use the second variation of the LRAM formula. So the left Riemann sum or rectangular approximation using 4 subintervals. The general formula is going to be using when the subintervals are uneven. The formula is simply going to be with 1 times f of x1 plus with 2 times f of x2 plus with 3 times f of x3 plus with 4 times f of x4. Okay? Notice how we started from 1 all the way to 4 and we omitted 5 because we're using the left endpoint. Okay? So let's apply this formula to this problem. It's simply going to be with 1 is 3 as determined above here times f of x1. x1 is 0 plus with 2 is 3 times f of x2, which is 3, plus with 3, which is 2.5, times f of x3, which is 6, plus with 4, which is also 2.5, times f of x4, which is 8.5. Okay? So this is a situation applying the LRAM formula onto our interval. Okay? So let's go ahead and now use the table. 3 times f of 0 is 10, plus 3 times f of 3 is 8. And then, well, let me make a real quick adjustment right here. You notice that in this problem, we are approximating the integral. Okay, so I should have written this, but I neglected to do that. So the integral from 0 to 11 of r prime of t dt. I was using f. In this case, f is r prime of t. So we're supposed to be looking at 3 times r prime of 0 plus 3 times r prime of 3 plus 2.5 times r prime of 6 plus 2.5 times r prime of 8.5. This is a function we are estimating the area under. Okay? So instead of equals, that should be approximated. Okay, so this is an approximation right here. So this expression is for the exact area, and what we have on the right side is an estimate. So let's put the estimation symbol there. Okay, so LRAM is an estimation of the area underneath a curve. And the curve we're looking at here is r prime. Okay, so let's go ahead and do what I had before. So we're going to have 3 times r prime of 0 is 10, plus 3 times r prime of 3 is 8, plus 2.5 times r prime of 6, which is 6.5, and then 2.5 times r prime of 8.5 is 5. Alright, so we just plug all these values in our calculator. Let's go ahead and do it. So what we have is, so your answer is going to be 82.75. So it's approximately 82.75. Okay? Alright, so the problem also asks us for, let's see what the problem asks. It says, state the meaning of your answer in the context of the problem with the units. Okay, so what does this answer mean? What did we just estimate? What is the estimated value of what we just calculated? Now, if you think about this expression to the left, what is this expression here? Using FTC part 1, remember, let's write this down on the side, that the integral from A to B of f prime of t dt is equal to, so the f prime there so you can see, is equal to the antiderivative of f prime, which is f, evaluated at b, minus the antiderivative of f prime, which is f, evaluated at a. Okay? So applying that to this scenario, the integral from 0 to 11 of r prime of t dt is equal to r of 11 minus r of 0. Okay? Now what is r of 11? This is the radius when t is equal to 11. What's r of 0? Is the radius when t is equal to 0. So what is r11 minus r0? This is the change in the radius. Okay? 82.75 meters. So what is the answer? What does our answer mean? This is the approximate change in the radius from t equals 0 to t equals 11. Okay, so that's a change in radius. It's going to be a negative change, but this is the change in radius from t equals 0 to t equals 11. Okay. All right, let's take a look at question number 4. It kind of looks like number 3, but it's totally different. So number 4, we had to find the integral from 0 to 11 of the second derivative r dot prime dt. Okay, so what's the difference between this one and number 3? Number 3 was we had the function, we're looking for the area underneath the function. Now we're looking for the area underneath the derivative of the function that we had from 0 to 11. Okay? All right, so how do we evaluate this? We do not have the table, but we have points here. So using the FTC part 2 again, this can be written as r prime of 11 minus r prime of 0. So the FTC part 2 is if you're integrating the function, you're evaluating the antiderivative at the upper limit minus the antiderivative at the lower limit, right? So in this case, the antiderivative of the second derivative is the first derivative, right? You just lose one of the primes and you get that. So we can use our table to finish this off. Okay, so what do we have? R prime of 11 is 4 minus r prime of 0 is 10. 4 minus 10 is equal to negative 6. What's the unit here? What are we calculating the difference between the first derivative, which is meters per minute? Okay, so it says what does your answer mean it with accurate units? Negative 6 meters per minute means that the change, change of what? What are we calculating the change of? The change in the rate of change of the radius, r prime minus r r prime at 11 minus r prime of 0. Okay, so we're calculating the change in the rate of change. Okay, so it means that the change in the rate of change, in the rate of change of the radius, rate of change of the radius is negative 6 meters per minute. Okay, so that's what we are calculating here. If you think about velocity, position, and acceleration, this can be viewed as a change in velocity. Okay, when you integrate your acceleration, you're dealing with change in velocity. Okay, so that's what we are looking at here.